All right, let's see, we have Connor is in. I'll wait a couple of minutes to see if who else shows up before we get started. We've got one more. Wait a couple more minutes, see who else shows up here. All right, we're about 5 minutes past our start time. I'm going to go ahead and get started. If anybody else shows up, we can catch them up when they get here. And we'll be sending out the slides and such for this later on, so they will be able to catch up that way if nothing else. So this webinar is about augmenting the Karpenter autoscaler in EKS with Platform 9's elastic machine pool. And we say augmenting because it is indeed possible, and in fact, there are some pretty compelling arguments that you get the best results when you don't use either one by itself, you use both of them together. At this point, I will also ask people to put their hand up if they can hear me okay, so that I know that I'm not talking to myself. Okay, I see Connor put his hand up. Fantastic. Always good to know. So, what is the agenda? We're going to go over some basic intro to me, to Platform 9, and to resource management basics in Kubernetes. And of course, that applies to EKS as well, which is mainly what we'll be talking about today. We're going to go over some of the basics of Karpenter, the prerequisites, how you install it, how you use it. We'll do the same for EMP, and we'll talk a little bit about the use cases that each of those does better than the other. They each kind of have their ideal use case that the other doesn't serve as well. So we'll compare those use cases to each other and also discuss kind of the mechanics of how you can keep them running together without stomping on each other. It's actually not very hard. So just as an intro, Platform 9 was founded in 2013. The co-founders were all early engineers at VMware. You know, most of them were early engineers at VMware. And they had this idea of starting their own company to, as they put it, democratize cloud computing, meaning make it possible for basically anybody to have the convenience of cloud computing without depending on a hyperscaler like AWS. So, oh, I see Omkar has come in. Omkar, you haven't really missed anything yet. Don't worry, I'm just introducing Platform9 and myself. I did go over the agenda, but you haven't missed anything critical at this point. So Platform9 has been around for going on 12 years. And we have a couple of major product offerings. We have managed OpenStack, which was kind of the foundation of the company, was to make OpenStack accessible to people who wanted to run their own OpenStack clouds. We also have managed Kubernetes. We have a managed KubeVirt offering. And then we also have this very new Elastic Machine Pool product. And that's what we're mainly going to be talking about today. So a little bit about me. I'm the technical product marketing manager at Platform9. I've been working with Kubernetes since 2015. I actually have a little bit of OpenStack experience in my background too. It's been a long time since I worked with it, day to day, but I was actually, when I worked at Red Hat, I was on our cloud practice consulting team. And the portion of the cloud practice consulting team that I was on dealt specifically and solely with OpenStack installs. But I've been working with Kubernetes since 2015. When I moved on from Red Hat, I went to work at CoreOS. And I already had a little bit of Kubernetes knowledge. And then when I went to CoreOS, of course, that was all Kubernetes all the time. And I've just kind of stuck with it since then. I've delivered a couple of sessions at KubeCon. I've got the list there. I will be at KubeCon Salt Lake City delivering another session. So if anybody attending is going to KubeCon in November, then you'll be able to see my session there if you have time to fit it in on your schedule. And just like our founders, I have some previous experience in large-scale VMware environments. And although we're not really going to be talking about VMware per se, that kind of environment is relevant to some of the issues and solutions to those issues that we're going to be talking about. So what are we going to cover? We're going to talk about basic Kubernetes resource management issues, kind of what the problems are and what everybody has tried to do to solve those problems up to this point. Then we're going to introduce some basic concepts and goals of Karpenter. So Karpenter is an autoscaler that was originally written by AWS. It is a public open source project now, but I think AWS is still the main contributor to it. Microsoft actually has their own fork of the project that runs in Azure. So it is, in some sense, cross-cloud at this point. And we'll talk about how you get it installed in AWS and how you manage it, how you get it to scale your workloads the way you want it to. Then we'll also talk about use cases that Karpenter handles well, use cases it doesn't, and we'll talk about how EMP can handle those use cases that Karpenter is not so great at handling. What we're not going to be doing, we're not going to necessarily get into a super in-depth discussion of how do I do this specific thing in Karpenter, or I'm having this particular problem in Karpenter, what is the answer? If you are having issues like that or you want specific advice on that, they do have a Karpenter Slack channel on the Kubernetes Slack. I am in there and I'm fairly active there. So although we won't really address those kinds of things in this webinar, there are places you can go and I am in those places. We're not necessarily going to go through an exhaustive discussion of all of the different configuration knobs you can tweak in Karpenter either, nor for EMP, to be quite honest. There's a lot of knobs you can tweak in both of those things, and we could fill up an entire day. And we're trying to keep this to about an hour webinar or so, with some time for Q&A. So the basic problem is resource management. And part of the problem is that workloads can request resources. Now, if you've been working with Kubernetes and you've been working in a cluster that has a lot of workloads deployed and there's resource contention, you probably already know about these basics like requests and limits. Well, the really annoying one is requests, because when a workload requests resources, Kubernetes just says, okay, you have that request, I'm going to give that to you. If I can't give that to you, I'm going to wait to schedule you until I can. Once those resources are assigned to that workload, it owns them. the requested amount of resources is owned by that workload until it terminates, or until Kubernetes terminates it for some reason. So one of the problems is that if a workload requests resources that it's not using, then they're just stuck. They're sitting there idle and nothing else can use them because that workload, just kind of owns them now until it releases them or until Kubernetes terminates it. Workloads can also consume additional resources past their requests up to those limits. So it makes it hard to scale because you can't just say, well, I'm going to give my workloads a minimal amount of resources and let them kind of take what they need without being aware that they may take a lot and therefore you need to set a limit. You also can't set a high request and say, well, okay, if it doesn't use them all, they'll be available to other things, because they won't be. If you give that workload more resources in its request than it needs, then, like I said, you're stuck. Now, as far as cluster resources, if you have either way more resource requests in your cluster than you have the ability to provide, you don't have enough nodes, or you don't have big enough nodes in your cluster, or the other direction. Maybe you have a really big cluster and there's not a lot of resources being used in it, being requested in it. So clusters need the ability to scale up and down, preferably automatically. This was something that actually, as we'll cover in a second, it came in very early because it was a very critical need and a lot of people requested it very early on. And so auto-scaling allows these workloads that request excessive resources to run, but you pay for that. If it's an on-prem cluster, you pay for it in the cost of the hardware you have to buy to run those additional workloads. If it's a cloud cluster, you pay in the hourly instance cost as those instances get auto-scaled up. How has the project tried to deal with these issues and find the happy medium between what applications want and what is actually able to be provided to them? Like I said, there's some scaling tools that came in very early. Now, one of the early scaling tools, and I believe it was right after the cluster autoscaler, was the vertical pod autoscaler. And so the vertical pod autoscaler is aimed directly at that problem of my application needs more resources than I've given it, or needs a lot less resources than I've given it. The VPA will actually rescale that workload's requests to be higher or lower as that workload's actual usage indicates that it needs. The problem with this is, and this goes back to the whole model of Kubernetes, until very, very recently, the only way to scale a workload like that, to actually change its resource requests, was to terminate it and restart it with its new configuration. So you incur disruption doing that. And that's not a great thing, particularly for some workloads that are very sensitive. Kubernetes has a whole infrastructure of resources basically designed to manage this. So you have things like pod disruption budgets. And you can say, okay, VPA, you can auto-scale this workload, but only so many pods are going to go offline at a time. That's great because it helps you make sure that you don't do things like lose quorum in a consensus cluster, but it makes all of this scaling take longer than it would otherwise if you could just do it instantly. Now, because of the disruption issue, there's now an alpha feature called in-place pod resize. But there's a couple of big caveats. One is that it's very, very early on in its history. It is not production ready. And even, the Kubernetes project maintainers working on it will tell you it's not production ready. I don't want to make any predictions, but I'm starting to see indications that in its current form, it may end up getting redone because of some of the issues that they're hitting. There are some indications, I think, that they're hitting architectural issues with the design of in-place pod resize, so that we don't know what the future of it will be or how far away that future will be. For cluster scaling, like I said, from early on, there's been the cluster autoscaler, but it's very, very slow, and it can be kind of expensive because of the way it manages nodes. Basically, what cluster autoscaler does is you, in your cloud provider, set up an auto-scaling group. Then you tell the cluster autoscaler, I have an auto-scaling group in AWS. This is its name. Here's, you give it some kind of credentials so that it can manage that auto-scaling group config directly. If the cluster autoscaler believes that you need more or less nodes in that node group, it then goes out and modifies that autoscale group. What that means is two things. Number one, the size of node that you get from cluster autoscaler is the same size as every other node in that group. Even if you don't need a node that big for what you need to run, you'll get a node that big anyway. And now you have unallocated but provisioned resources. This is another problem besides the allocated but unused resources. And because of that, it can be expensive because people want to say, well, okay, to make sure that my big workloads can run when they scale up, I want big node sizes to be auto-provisioned. But now you have to pay for those big nodes. Karpenter came along a few years back. I only started hearing about it maybe a year or two back. But Karpenter came along around 2018, 2019 and said, we can improve on this. Number one, rather than just say we want to auto scale to provide additional resources, another goal of Karpenter is to make sure that those resources are provided as inexpensively as possible. The other thing that it does is it doesn't leverage cloud provider scaling groups. It just provisions nodes itself, and it will actually look at, and this is right now Karpenter only, the Karpenter upstream project only supports AWS EKS. What it will do is it will reach out to the AWS API. It will say, what kinds of nodes can I provision? What kinds of instance types can I provision? And then it will pick the smallest node instance size that fits with what it needs to actually allow to schedule. So if you have a tiny pod, just one tiny pod that needs to schedule, you'll get one tiny node. And so that can be nice. And because that can lead to a profusion of different kinds of nodes, and that in itself can be somewhat inefficient, another thing that Karpenter does, besides trying to provision nodes as cheaply as possible, is it does try to look at things like, oh, if I consolidate these 5 nodes into one bigger node, then it'll be less expensive, and it will try to do that. Again, though, to do some of these clever things, you have to incur disruption. There's no way for Karpenter to consolidate workloads from a set of nodes onto a single node, or move them from a more expensive node to a less expensive node without letting them be terminated and restarted. And so with that termination and restart, you're back to incurring disruption again. So it can be difficult to manage, and Karpenter has its own, in addition to the Kubernetes resources like hot disruption budgets, Karpenter has its own things like you can schedule when disruption is allowed to happen in a Karpenter node pool. It's a great feature to have, but it makes managing things more complicated. So let's talk a little bit about the basics of Karpenter. But before we do that, I'm going to pause for a second because we do have a couple of people in now. Does anybody have any questions about what I've covered so far? Go ahead and just put them in the chat and I'll see them there. And if not, just go ahead and give me a thumbs up or put your hand up and let me know that I can go ahead and go on. Let's see. Sanika's got a hand up. I'm assuming that indicates that I'm good to go there. All right. I'll give Car and Connor a moment in case they need to get to their keyboard, and then we'll move on to talk about Karpenter basics. Okay, Amkar says he is good to go. Okay. Oh, all right, all good. Everybody says we're good to move on. So let's talk a little bit about Karpenter. I already talked a little bit about this when I was comparing it to Cluster Autoscaler, but let's kind of recap. It gives you more flexible scale up than the Cluster Autoscaler does, in terms of it can choose a variety of instance types instead of being limited to whatever instance type is in the node pool that's going to be scaled. That's another thing about the Cluster Autoscaler, by the way. There is a relatively high administrative burden for that because you have to go out and set up that autoscaling group in your cloud provider yourself, and then tell the cluster autoscaler about it. With Karpenter, you don't have to tell it anything about any cloud provider scaling group. It just goes, this is the size node I need. Hey, cloud provider, give me that size node. And then it registers that to your EKS control plane as a worker node. Karpenter will try to consolidate these workloads, meaning it will try to do a few different dimensions of consolidation. One, if it can replace a more expensive node with a single cheaper node, it will do that, unless you're not allowed to incur that disruption for some reason. It will also try to consolidate multiple nodes into a single node that is less expensive than those nodes together. So, and it does some, fairly detailed calculations. It tries to take into account things like taints and tolerations, or topology constraints, or what's the other thing I was just thinking of? I can't remember the other thing, but it basically does a scheduling simulation and then says, yes, this would successfully all schedule onto this cheaper node, and therefore it's going to disrupt, it's going to, spin up the new node, and then when it's ready, it will terminate the old node that it's being consolidated from. The other nice thing about Karpenter, and this was probably the reason that most people started using Karpenter in the beginning, was Karpenter has native support for EC2 Spot. So what that means is that Karpenter can provision Spot instances. And when you're using Spot instances, you have that, you may get a termination notice, right? And when that termination notice happens, that's your 2-minute warning that that instance will be going away and there's nothing you can do about it. Karpenter will provision those Spot instances, and then it will actually watch for those termination notices. And if it sees one, it will provision additional capacity so that when that Spot instance terminates, there's already capacity ready for those workloads to migrate to. So you can use Spot with the cluster autoscaler, but it's a little more involved because you have to actually have a separate component called, I believe it's called the termination handler. And the termination handler actually does the details of watching for those Spot termination notices. So how do you configure Karpenter to manage all this stuff? Well, there's a couple of different things, and the way I think of them, you can see that on the last bullet point of each of these, is one of them is from an AWS perspective, what do the nodes in this node pool that I'm configuring look like, right? So it's things like, what AMI are you going to use for it? When the kubelet service starts up on that node, how is that service going to be configured? What subnet is that node going to show up in? What security groups are going to be assigned to it? This is all the kind of stuff that, if you're familiar with CloudFormation or Terraform provisioning in AWS, you've done all this before when you spun up EC2 instances. That's kind of what Karpenter puts into the EC2 node class resource. And so you define the AWS characteristics of your node classes that you want Karpenter to support. Then for individual nodes, there's a node class, and then there is a node pool. One or more node pools can reference the same node class. And the node pools are more oriented around, what does this node look like to Kubernetes? So it's things like lifecycle management. That's kind of on the boundary between Kubernetes management and AWS management. Labels in Kubernetes, taints in Kubernetes, that kind of thing. Basically, when this node registers to the cluster, what does the cluster see? Is this node's config? And the node pool resource is also where you configure things like, I want to allow these specific instance categories, instance types. I want to allow or disallow Spot provisioning for this node pool, etc. I mentioned that Karpenter has its own scheduling and disruption controls. It will account for scheduling constraints when it's provisioning nodes. So it actually will look at what constraints Kubernetes puts on that workload scheduling. And one of the important things about that is that if Karpenter sees that there's no way to provision a new node in such a way that those scheduling constraints can be met, it won't do anything. So there are situations in which Karpenter says, nothing that I can do will move the needle on this, therefore I will do nothing, because it wouldn't make sense to incur additional expense. It does respect those pod disruption budgets. And what it does under the hood, you can see these, but you aren't meant to manipulate them yourself. In addition to the EC2 node class and the node pool resources, it creates and monitors its own resources called a node claim. So basically what it says is, all right, I need to create this node with these characteristics. It creates a node claim for it, and then it goes out to the cloud provider and says, create me this node. And then when the cloud provider reports that that node's been created, it comes back and updates the node claim so it knows this node claim has now been satisfied. So the node claim is basically its own kind of internal accounting. You can see it though. So if you're having trouble with Karpenter and you're trying to figure out, well, what's going on here? How far did this get? You can look at the node claim resource for whatever node is supposed to be provisioned. If you delete a node claim, that causes the actual node to be deleted. If you delete the node, that causes the corresponding node claim to be deleted. And the node claim is owned by a particular node pool. So if you delete that node pool, then it causes all of the node claims owned by that pool to be deleted, and that in turn causes the nodes to be deleted. So what Karpenter needs at a high level? And I break this down a little bit differently when I go through the actual, there's the Terraform provisioning lab that I did for Karpenter a couple of weeks ago. And I broke this down because in that lab, it matters what provides each piece of this. But at a high level, there's a few things that Karpenter needs. And since we're not talking about specific provisioning methods here, I can fit this all in one slide. Outside Kubernetes in AWS, you need an AWS role, some kind of credential to allow Karpenter to provision and destroy those nodes. I mean, if you can't do that, then Karpenter really can't do anything for you. If you're using Spot, and I believe only if you're using Spot, if you're not using Spot, you don't need these. You need EventBridge, which used to be called CloudTrail, I think was the name for it. And you need an SQSQ. Say that 5 times fast. What Karpenter uses that SQS and EventBridge for is the EventBridge rules watch for those Spot termination instances. Then EventBridge pushes them into the SQS queue, and Karpenter watches that queue for those termination notices to come through. And then that's when it does its, workload migration magic to make sure that your workloads at least have a place to land. Inside Kubernetes, of course, we have the CRDs to define those resources that I mentioned on the last couple of slides, the EC2 node class, the node pool, the node claim. There is a running controller that sits there and monitors the config resources that you create, takes actions when it needs to take actions. There is identity mapping. There are multiple ways to provide Karpenter with the credentials it needs. The current preferred one is to use the pod identity mapping feature in EKS. And that grants Karpenter access in the cluster based on the AWS role that you assign to it to use. And then, of course, Karpenter creates the CRDs, or I should say the Karpenter Helm chart, creates the resource definitions for node pools, node claims, etc. Then when you're actually operating Karpenter, you will create the actual node class, node pool resources. Karpenter, of course, creates its own node claims. And if you don't configure anything, Karpenter just won't do anything. It'll sit there and wait for you to tell it what to do until you do so. So the install for Karpenter, it's usually a 2-step process. You pre-provision those AWS services if you're using them, the queuing service queue and the EventBridge rules. You do need to provision those AWS credentials in whatever form is necessary for your environment. And then once you've created those prerequisites, those resources and credentials, you install the Karpenter Helm chart And it will assume some default values. So if you create the prerequisites with all those default values, then you don't need to really change much with the Helm chart. If you do things like give things different names or you want to install things in different namespaces, you may need to alter those Helm chart values. And there's a couple of different ways you can do that. I don't want to necessarily get into the details of Helm here, but you can either have Helm manage the CRDs for you by using a separate chart, or you can have Helm just install them as a one and done, and then you manage them yourself in the future if they need to be upgraded. So, all right, we've talked a lot about kind of the nitty-gritty technical details of Karpenter and how you get it going and, what it's for. What are the good scenarios for Karpenter? Let's give it its due, right? It's very good at managing scaling for workloads that can tolerate disruption. I mean, that's kind of Kubernetes' main ideal use case is you have those what people call 12-factor app workloads. They're stateless, they're tolerant of disruption, they scale up and down very quickly. Kubernetes is good at managing those, and Karpenter is good at managing auto-scaling for those. If you have workloads that do tolerate disruption like that, and you have workloads that don't tolerate disruption, as long as they're well separated, they're in different namespaces, or they may be in different clusters entirely, or however you want to manage it, it's very easy to configure Karpenter to only manage the ones that are good for it to manage. Now, that doesn't mean you can't manage those others with it, but they're just not the ideal workloads for it to manage. And then this third thing is really important from a Karpenter's perspective. You want everything to have well-defined, efficiently set resource requests. And that includes not just the things Karpenter is going to manage, but also other workloads on your cluster. One of the common scenarios that I've seen is people say, well, Karpenter provisioned a node so that I could, I scaled up a deployment. Karpenter provisioned a new node so that that deployment could land on it. And then nothing happened. My workload still just sat there waiting to schedule. One of the common scenarios for that is there's a daemon set that has no resource request set. So to Karpenter, it doesn't know how much it needs. So it can't account for that when it's provisioning the new node. And then when the new node is provisioned and the daemon set starts, it consumes enough resources that the node no longer has enough resources to run the workload that Karpenter put it there to run in the first place. So to avoid those kind of scenarios, you want not only your Karpenter workloads, but all of your other cluster workloads to have well-specified resource requests. Not too high, not too low, something that Karpenter can look at and go, all right, I know how much this is going to take up when it lands. Challenging scenarios for Karpenter, basically everything that is not those things. You have workloads that are defined inefficiently, where you have a lot of resources that aren't being used, or you have the workload has a low resource request, but it turns out it actually needs a lot more than that, because that workload, like I said before, will be allowed to take up more resources up to a limit. And so there are scenarios where Karpenter provisions a node that is just big enough for what it thinks the workload's going to need, but then when the workload actually lands and starts taking up the actual amount of resources it needs, it exceeds its resource limits, or it exceeds what's available on the node and gets evicted. If you have workloads that can tolerate disruption and they're kind of mixed in the same namespaces with workloads that can't, there are ways to handle that, but they require a little more effort from you. It's not as seamless to get Karpenter to do that itself. You have to start using things like taints and tolerations a little more aggressively. And then, like I said, you run into those scenarios where daemon sets, resource requests are not specified. And so you get into this cycle of nodes being provisioned, nothing lands on it, it's underutilized, it gets disrupted, a new node gets provisioned, etc. One of the things that Karpenter doesn't try to do, a non-goal of Karpenter, so I don't say this is a deficiency because it was never a goal of Karpenter in the first place. If you have a workload that requests a lot more resources than it needs, just like with cluster autoscaler, Karpenter does not try to resize that workload. It will happily scale up the amount of resources you need for that massively overspecified workload, and then you end up paying for those resources. That's not Karpenter's fault. That's what else can it possibly do? It doesn't know what the workload is actually going to use. It just knows what the requests are, and so it does its math based on requests. So again, I'll pause there, see if anybody has questions. Go ahead, give me a thumbs up or something to let me know that we're good to go. Give people a minute to get to their keyboards. All right, I'm gonna assume we're, oh, okay. Let's see. I see Connor said he put a question in Q&A. Oh, I haven't even been looking at the Q&A. Let's see. Yes, there are patterns, but like I said, I will cover that in the Q&A at the end. But yes, the basic answer is yes, and we'll talk about that. Anybody else? Going once, going twice. All right. So let's move on with basics of EMP. Now I gave you kind of the three boxes for the Karpenter key features. The EMP key features are non-disruptive workload consolidation. That's the big one. EMP can consolidate these inefficient workloads, exactly the kind that Karpenter will auto-scale to allow to schedule, but it doesn't make them any more efficient. EMP, and we'll talk about how it does this in a minute, essentially resizes those workloads on the fly without disruption, without depending on that alpha in-place pod resize feature. We're going to talk about how it does that magic in a little bit. The other thing that's nice about EMP, it's a SaaS product. There's a console-based management, web interface. It's very user-friendly. We're improving it all the time. We're aware that, there's never a time when you can't make another improvement, right? So we're always looking at what people are trying to do, what people need from the product, and how can we make that interface better. It also has kind of self-service authentication. You can authenticate to that SaaS product console through your existing Google Workspace account, which is nice for people who are, using EMP for production workloads for real enterprises. So EMP also has kind of a two-level scaling configuration. In this case, it's divided up into a bare metal pool, and then on top of those bare metal, you can have one or more bare metal pools, just like with Karpenter, you can have one or more EC2 node classes. Then on top of your bare metal pools, you have elastic virtual machines in pools, and we'll talk about what an EVM is in just a minute. Those EVM pools are associated with a bare metal pool. That bare metal pool has a virtualization layer built on top of it. And so what you have is essentially a virtualization cluster built on cloud bare metal that is then these EVMs, these elastic VMs are being provisioned out of that hypervisor cluster, and those get registered to EKS as worker nodes. So why do we do this way? Because what this allows us to do is we go ahead and provision these EVMs. And in fact, when you look at them, we give them size names that roughly correspond to what an EC2 instance would be in terms of RAM and CPU and so on. So we just go ahead and provision more EVMs as workloads need them to be scheduled. But the trick is, underneath of that, in the bare metal pool, we are able to use overcommitment of these VMs. We can say, because we can see, oh, well, so much RAM was allocated to workloads running on this node, but 90% of it's unutilized. It's just sitting there idle. We can consolidate away that idle memory and just keep packing them in until we hit, obviously we don't want to pack it to 100%, but we pack it to a designated threshold of overcommitment. And then if we need additional resources, we scale up additional bare metal in that pool, and then we can provision more EVMs and the process repeats. The other thing that this allows us to do is say, okay, we kind of packed EVMs onto a bare metal node. Now the resource consumption on one of those EVMs has gone up. It needs more resources than are actually going to be available. We're hitting that threshold. What we can do is we can live migrate that virtual machine with that running pod in it over to a new bare metal machine. And that pod never really has any idea that anything is going on underneath it. It doesn't even know that it's moved between one physical node and another, because from the pod's perspective and from Kubernetes perspective, that node or that pod has just kept running on the same node that it was running on. So what do we need for this? Well, as you might expect, we need some of the same things that Karpenter does, because we're doing some of the same things. We're provisioning infrastructure in AWS. That means that we need an AWS credential. And we need to be able to access the AWS APIs to do that, so that we can provision and destroy those bare metal instances. Because of the way we manage these things and build that virtualization layer and such, we also need an SSH key to be provided. Now, right now that's provided for the bare metal, it's provided as an AWS key pair. For the EVMs, it's provided as just an SSH public key, and then we embed that into each one of those so that EMP can do its management magic. The other thing is, because it is a SaaS product, we need security group rules to allow the EMP SaaS control plane to connect to the cluster API to monitor and manage all this. Now, the nice thing about that, you'll notice I put an asterisk there. That's because if you allow it to, EMP will just go ahead and make those changes itself. You just tell it which security group you want to add those rules to, and it will go out and do it using that credential that you gave it. So that part of it is actually, it's a requirement that EMP can self-serve there. Inside Kubernetes, again, there's a couple things we need inside Kubernetes, but not as much, because the way EMP works is totally transparent to the Kubernetes control plane. We don't need any CRDs. We don't need, any custom resources. We do install a webhook, and so we need an RBAC configuration to allow that webhook to access the cluster API. And there's also configuration that you can put in. One of the mechanisms that you do need to worry about is a config map. And so that config map tells EMP which workloads you want it to try to scale onto elastic machine pools. And again, if you don't have anything, there actually are one or two cases that we do auto scale in there under certain circumstances, just for the health of the cluster itself. Because if we didn't do that, then EMP's webhook itself wouldn't be able to run or operate. So, but by and large, the config map inside the cluster determines 100% of which workloads end up on elastic machine pools. And there's a reason for that, because there are some limitations with EMP. We don't want to schedule workloads onto EVMs that won't be able to run. For the cluster support, we do support Amazon EKS. You are currently required to use the AWS VPC CNI, the cloud networking interface, ClusterNet. I forget what CNI actually stands for. You can currently only run basically x86 workloads. I put x86 64. Some people call it AMD 64. I don't know if anybody's still running 32-bit workloads in EKS, but if you are, why? You do need specific load balancer configuration. Your load balancers have to be elastic load balancers or network load balancers, and they have to use an IP target type. And that's because the other target types, one of the more common target types is instance ID. Well, EVMs don't have an instance ID. So that's one limitation there. But that's for a lot of workloads, all you have to do is change your load balancer configuration. And in Kubernetes, that can be as simple as changing an annotation, and then off you go. You're ready to go with EMP. This one's not a hard requirement, but it's a best practice. You want to use IO2 types for any EBS volumes that you're using. And the reason for that is if you're provisioning volumes from EBS for your Kubernetes workloads, if we live migrate the EVM that those pods are running on, we have to migrate those volume attachments. And the IO2 volume attachments can migrate faster. And if somebody's curious about why, I can go into the technical details toward the end when we do Q&A. But essentially, if you use other EBS volume types, they will still migrate. It will just take them a lot longer to do so. So you want to use IO2 when you can. Now, I mentioned that we only currently support Amazon EKS and those x86 workloads. On our roadmap, we are working towards supporting additional clouds. We're working towards supporting additional architectures. Everybody's excited about Graviton. Everybody's really excited about GPUs, and those are both on our roadmap to be supported by EMP. So how do you install this thing? Well, it actually looks a fair bit like installing Karpenter, at least in the first bit. You're going to pre-provision those AWS credentials, and you can automate that with CloudFormation. We actually have a CloudFormation template in our EMP docs that will provision a credential with the required naming. There is a name that we use, a name format we use for auto discovery of credentials and other things, and make sure that it has the proper permissions. So you create that credential in AWS, then you log into the EMP console and create, we call it a cloud provider. It's basically just putting that credential into EMP. And then you follow the console install wizard. It walks you through the process, and it gives you this very nice status display of how everything is going. Now, one of the things that I want to cover is the idea that, as we mentioned before, we intend, and we in fact believe that the best case, at least I believe the best case, is that you're going to be using Karpenter and EMP together in your cluster. Karpenter can handle those GPU workloads. Karpenter can handle those Graviton workloads. It will select the right instance type to run those. And so, if you're running Graviton, if you're running GPUs, if you're running other things that aren't really suitable EMP workloads right now, by all means, please do install and use Karpenter to run those workloads. Then run the things that Karpenter doesn't do well, those inefficient workloads that have really high requests. And you might say, well, why don't I just change the requests? Well, in one case, it may be that they're separate teams, and one team specifies the requests and one team just implements. And if you're the team that just implements and you aren't allowed to change the configuration, well, what are you going to do? You're going to run EMP. That's what you're going to do. And you can keep those workloads separate by, like I mentioned before, you can use taints and tolerations to make sure, in fact, by default, EMP configures a taint on all the nodes that it provisions, all the EVMs that it provisions and registers. So by default, your workloads will not migrate to EVMs until you alter them to add that toleration. Now, again, there's that config map that you can configure, and you can say, I want EMP to auto-inject that toleration as a webhook for workloads that meet this criterion. And that can be, it's running in a particular namespace. It can be that it has a certain set of labels. There's a fair bit of flexibility there. But to automate that process, you can use that config map to configure the webhook. And then, what we recommend is kind of a gradual migration. You test things, make sure they're going to work well in EMP. You go ahead and add the automatic configuration for them to that config map. Eventually, you've got everything over there that you need to run over there. So Before we do the Q&A, my original plan for this was that I was going to do about a 5 or 10 minute demo of EMP playing nicely with Karpenter. Unfortunately, I ran into what appears to have been a transient error in AWS provisioning bare metal in US East 1. I know, the demo gods were not with me today. But what I am going to do is I'm going to go, make a second attempt. Hopefully it will, like I said, it was just a transient error, and the second attempt will just go completely fine. And what I'm going to do is record that, and then we'll post that recording somewhere on our website or on our YouTube channel. And we're going to send out an email after this webinar is over with the slides and, some follow-up info. And we'll make sure that video link either goes into that follow-up email or maybe a separate one if it's something that takes a little bit longer to resolve. But hopefully when that email goes out later today or possibly tomorrow, that YouTube link will be inserted in it, and you'll just be able to watch that demo just as you would if I was doing it live. So with that, we'll go ahead and do Q&A. And I see that Connor has asked our first question: are there opinionated or well-known patterns for introducing Karpenter in place in an existing EKS cluster? Or do people typically follow a blue-green switch where a newer cluster is brought up with Karpenter and workloads are migrated? I have done it mostly the second way, because I feel like that is actually, when I do demos and workshops based around Karpenter, I feel like that's actually more realistic, that you're going to have a cluster. And you don't necessarily want to have to build a whole new, a whole new cluster just to migrate those workloads over. It is possible to do. There are a couple of things you have to make sure. You have to install the pod identity add-on for EKS. You have to create an EKS access entry for the credentials that Karpenter is going to use. There's one or two other things that need to be done. The other thing you have to do is you have to tag your subnets that you want Karpenter to use for provisioning nodes. That's also, that's something you can do after the fact. In fact, I recently discovered when I was looking at this, if you're using Terraform, you don't even have to alter your original Terraform that you used. Terraform actually has this weird little resource that manages just the tags on an existing piece of infrastructure. So you can say, configure a data source to identify a subnet or a set of subnets, and then you can use that tag resource to apply tags to them, even if Terraform doesn't manage the underlying resource itself. It's actually really kind of neat. So it makes it very easy to provision Karpenter in an existing cluster, even if you didn't set that cluster up with Karpenter to begin with. That said, if your cluster has been around a long time, if your workloads have been running there a long time, it may be worthwhile to at least examine the idea of, should we rebuild this cluster from scratch? We've been running this production EKS cluster for 3 years. What would be the level of effort? What would be the level of downtime or other disruption that we would incur if we did this? And would there be benefits to doing it that outweigh that? I feel like 9 times out of 10, the answer to that question is no, just keep going with what you already built. But every now and then you get that 1 out of 10 where you go, you know what, if we do this, if we rebuild this, we can cut our cost in half, or we can cut our admin burden in half or something like that. So it's case by case. You can do it either way you want. Any other questions? I can actually allow people to speak. Let's see, I can allow you to speak. I can allow you to speak. So, all right, I've enabled everybody to talk. If you want to just unmute your mic, if you have any questions, you can go ahead and just ask them live. Or if not, just go ahead and give me a thumbs up or put something in the chat like I'm good.
I have no more questions, but I'll give you a thank you for the answer to the previous question.
Yeah, sure. And all right, so that takes care of Connor's question. If anybody else has any, going once, going twice. We're actually just about at an hour now, which was right about where I wanted this webinar to land. So with that, I will go ahead and wrap up. I did not forgot to put my final thoughts on this slide. The basic final thought that I put on things like this is you don't have to use Karpenter. You don't have to use EMP. There may be certain reasons that you would or would not want to use one of those on a particular cluster, or you might not want to use either of those on a particular cluster because of what it's running, or because you don't want to touch it in the ways that you would have to touch it to configure it to run one of these additional autoscalers on it. That is, I don't judge people for saying the level of effort or the level of risk that would be involved in that is more than we want to incur. In those cases, though, going back to my answer to Connor, I would say take a look at whether you should build something, a replacement from scratch. Because if the risk is in touching the existing thing, you're taking that risk anyway. There's going to come a day when something is going to happen and it's going to require you to change that cluster configuration in one of the ways that you would have to do. And if you haven't already evaluated the risk and benefit of doing that, then you're going to be taken by surprise and you're going to be scrambling to figure out what to do. So just because it's slightly risky and you don't really know what that level of risk is, isn't a reason to just go, well, we're not even going to try it and look at it. Go ahead and look at it, figure out what makes sense for your workloads, what makes sense for your clusters, and then move on from there. Slides and other info will be sent. There's a link to the Karpenter docs in these slides. I'll add a couple of other things that occurred to me as I was going through here. And so when you get the copy of the slides, this one will have a couple of more links in it, including the EMP docs, the EMP console link so you can sign up. Obviously, this whole thing is sponsored by Platform9 Elastic Machine Pool. It is our newest product. It is actually, I feel like it's a really kind of cool product. It is taking what used to be what is actually a very old answer to a very current problem and saying, hey, guys, we already know how to do this. We just got to actually sit down and do it. We know about VM overcommitment. We just have to figure out how to apply VM overcommitment to this use case. And our engineers sat down and did it, and it works, and it's really awesome. So thank you. Like I said, we will send out the slides. I will make sure that demo link gets to you. Last chance if anybody has any final questions. I see Amkar already left, dropped off, but Connor, if you had any more, or Sanika.
Thanks a lot. I guess based on your previous answer, if you're stuck on EKS 1.25 and you're paying an extended support charge, maybe it's time to consider introducing Karpenter in a greenfields cluster, like you said, I guess.
I would say so, yeah. And
Yeah.
that was one thing that I didn't get into in the requirements for EMP. We are trying to make sure that EMP supports all of the currently supported AWS cluster versions. So the current list is EKS 1.27 to 1.30. So, if you're running that old 1.25 cluster, Karpenter actually has some version skew limitations there as well. Older versions of Karpenter will at least complain about newer versions of Kubernetes than were current when they were released. Sometimes they will not work. Sometimes it will just throw a complaint in the logs, but everything will work fine. So, with both of those, you're taking a little bit of a chance, and you definitely need to test if you're running an older version. Will this work? Maybe, maybe not.
Gotcha. Thanks a lot.
Yep. Sure thing. And with that, I'm going to go ahead and close it down. Thank everybody for coming. And you'll get that follow-up email today or tomorrow.